So good morning, good afternoon, good evening, depends on where you are in the world. So we are here today to attend a very nice talk by Dr. Elisabetta Moisello from University of Pavia, Italy. But before giving the floor to her, just some brief announcements. So if you lost some of the talks that were done since mid-2022, there is more than 150 talks available in this YouTube channel, so all free. Then next beginning of September, as you know, we have a huge flooding in the south of Brazil, and then in micro that was scheduled to May, the microelectronics school is moved to end of September. So we are going to celebrate 40 years of the symposium and 25 years of the microelectronics school. Then next year is a great opportunity to come to the south of Brazil, to the most traditional wine region at Bento Gonçalves, very close to Porto Alegre. And as you know, as a flagship conference of CASS, a selection of best papers are invited to have the papers in TCAS 2 and TCAS 1. So the one selected for TCAS 2 appears in the edition of the months of the conference. And during the conference, there is an extra evaluation to invite the papers to submit extended version, 11 page, for example, to TCAS 1 in a special issue. So the deadline was extended to next September 20, so you have about 2 weeks to finish your papers to submit it to this edition. And together of last, we also do the Iberchip, so it's a 31 edition of the workshop, where students also researchers can also submit papers, not only in English, but also in Spanish and in Portuguese. So this we will have also a deadline extension. Then 2026, Lascas goes to Peru, to Arequipa, very nice location also. And 2027 to Panama City, as you can see by the photos, also a nice region. On the left, in the top here is part of the Panama Channel, that is an impressive system. And we are just finishing the Chip on the Cliffs, SBCCI 2024 this week. So next year, we are going to be back to Manaus. The first edition Manaus of the Chip in the Jungle was year 2000, so 24 years ago. So next year, we are going to celebrate the 25 years of the set of chips in something conference. So as you know, this is also co-sponsored not only by the Brazilian Society, but also by Circuit and System Society and Calcium EDA. And you have till end of March to submit your paper. So it's being prepared a very nice and special edition. So it's a great opportunity for you to know the Brazilian jungle, and it's very nice. So together with SBCCI, we have some other collocator conference, SB Micro, workshop on circuits and system, Insist Student Forum, and also Chip Inclusive that is dedicated to students of the school. So it's another activity that will be done together. And end of April next year, we have the first edition of the Latin Conference on Internet of Things, that is an IEEE IoT Technical Community Flagship Conference. So this will be the first edition. The IoTTC is composed by 12 IEEE societies, including CASS, and for sure proceedings published in IEEE Explorer and so on. The second edition should be in Colombia, and probably the third one in Chile. So this will move around Latin America. But we are here today to attend the talk by Dr. Elisabetta Moisello, talking about integrated interface circuits for MEMS contactless temperature sensors. So Elisabetta Moisello was born in Pavia, Italy in 93, in 90s, in 2017 and 20 respectively. She received the master degree in electronic engineering and the PhD in microelectronics from the University of Pavia, where she is currently a postdoctoral research fellow and contract professor. Her research topics include sensor interface circuits, switching, DC-DC converters, and wireless power transfer. She has been and still is part of the organizing committee of the Prime Conference and has served on the technical program committees of several international conferences like Prime, ICCS, and UCASS. She is an associate editor of the IEEE Transactional Sequencing Systems, Part 2, express briefs that, as I told before, is there is always some selected papers from LASCAS that are included in TCAS2, and she is an IEEE and CASS member, and she's currently serving on the CASS Board of Governors as a young professional representative. So thank you very much, Elisabetta, for accepting our invitation, and the floor is with you to start your presentation.
Thank you. Thank you for the very nice introduction. Today, I will talk about what has been the topic of my PhD, that is integrated interface circuits for MEMS contactless temperature sensors. This is an outline of my talk. I would start with an introduction on the different types of thermal detectors and how they work. Then I will focus on the two test chips I developed during my PhD, one for a thermopile sensor and the other for a novel type of thermal detector that it's called TMOS. And I will describe the proposed interface circuits and provide measurement results considering both the case of contactless human body temperature measurements and the case of presence and motion detection applications. And finally, I will conclude my talk with a comparison between the two proposed systems. So starting with the introduction, all thermal detectors rely on the Stefan-Boltzmann law that says that every object emits thermal radiation depending on its temperature. So by detecting the thermal radiation, it's possible to implement contactless temperature measurements. In the last few years, Internet of Things, smart homes, wearable and mobile devices have gained considerable interest. So the research in this area has been pushed towards low power, low cost, CMOS compatible solutions that can be employed in those applications. In particular, there is an interest on performing contactless fever measurements. So for these kind of applications, the main requirements are repeatability and accuracy within plus minus 0.3 degrees Celsius. And the other area of interest is the one related to, let's say, security and automatic activation of appliances and so on by relying on presence, motion, and proximity detection. As I mentioned, there are different types of contactless temperature sensors. The main ones are the bolometers, the pyroelectric detectors, the thermopiles, and this new device that is called the TMOS. Before going into details about the different type of thermal detectors, we need to see some basics about thermal detectors theory and the parameters that are used to evaluate the performance of thermal detectors. The main parameter that is used is the responsivity R, which is given by the ratio between the output signal produced by the sensor and the incident radiant power on the sensor. The incident radiant power depends on the Stefan Boltzmann constant, on the emissivity of the source object and the detector object, on the area of the detector, and also, of course, on the temperatures of the detector and of the source object, and also on a coefficient that it's called FSD, which depends on the geometrical arrangement between the detector and the source. For example, if we consider the geometrical arrangement in the figure, the FSD coefficient as the expression in the slide, which is the expression I will be using also in the measurements I perform with my system. Another parameter of interest is the field of view, which is defined as the solid angle in which the detector is sensitive to radiation. And this field of view can be, let's say, unlimited, and or can be limited by optics and caps. And in that case, if the source object completely fills the field of view of the detector, what can be seen is that basically the sensitivity will no longer be dependent on the distance between the object and the detector, as long as the source object completely fills the sensor field of view. And this will be a condition which we will see is used during measurement. Another parameter of interest is the so-called response time, which is given by the ratio between the thermal conductance of the detector and its thermal capacitance. And this gives an overview of, let's say, the speed with which the sensor can respond to detected radiation. Now, looking at the different types of thermal detectors, the most, let's say, common, the most old one is the bolometer, which basically consists on a resistive element whose resistance value varies with temperature. So there is typically an absorbing membrane which collects thermal radiation, which in turn determines a variation of the temperature, of the local temperature of the device, which will affect its resistance properties. The bolometers can be realized using different materials. For example, vanadium oxide and amorphous silicon are the most used, but they have the disadvantage of requiring complex fabrication process steps, which are not compatible with standard CMOS. And so bolometers are not quite good when it comes to, let's say, integration. Then aluminum is compatible, but has poorer performance. And recently, there has been also a focus on trying to develop bolometers employing organic materials. Then we have the pyroelectric detector, which is an AC device. Basically, it functions in a way similar to piezoelectric devices, in the sense that in the case with piezoelectric, that depends on, let's say, pressure. Here, it depends on temperature variation. When there is a variation in temperature, there is a polarization in the material, which can give rise to an electric current. But this happens only in the case that the incident radiant power on the detector is varying. So if these are quite good for performing, let's say, motion detection by trying to detect, for example, a person that is moving in front of the sensor. But these are not good for implementing absolute temperature measurements because in that case the object would be fixed, and so optical or mechanical chopping is required in order to use those sensors in that kind of application. Then we have thermopile sensors, which are made up by a certain number of thermocouple elements placed in series, where each thermocouple element consists of two different conductor materials forming two electrical junctions, which are at different temperature. One is the cold junction, and the other is the hot junction. The cold junction is basically placed at a reference temperature, while the hot junction is the one whose temperature we want to, let's say, we are interested in measuring. Thanks to the Seebeck effect, when there is a temperature difference between the two junctions, electrical potential delta V, which is proportional to the temperature difference between the two junctions, originates. In particular, when we look at a thermopile, we have that the hot junction membrane absorbs the thermal radiation, which is emitted by the target object, while typically the substrate constitutes the cold junction. Then we have the most recent type of thermal detector, which is the so-called TIMOS, which has been developed by a research group in Technion Institute of Technology, and has been fabricated by ST Microelectronics, which consists of a 130 nanometer CMOS SOI transistor, which is subjected to MEMS post-processing in order to obtain suspended transistor, which consists of a thermally isolated structure released by dry etching. In this way, there is the absorbing membrane, which collects the thermal radiation from any target object. And this determines a local temperature variation in the membrane, and so in the transistor, which in turn determines a variation of a transistor current voltage characteristics. Of course, the performance of the TIMOS will depend on the configuration of the transistor and its operating point. So, summarizing, looking at the various types of thermal sensors, what we see is from the point of view of integration, pyroelectric detectors, the so-called PIR, are not very good because they may require optical or mechanical chopping, which would make them very bulky. And also the integration properties of microbolometers are moderate because of the additional process steps required when employing the materials like vanadium oxide or amorphous silicon, which are not strictly compatible with the CMOS processes. This, of course, relates to also disadvantage of these two types of detectors when it concerns cost, while they provide a moderate sensitivity. On the other hand, thermopiles and the TIMOS can be integrated quite easily at a very low cost with a good sensitivity for the thermopiles, which can become very high in the case of the TIMOS when the intrinsic active gain of the transistor is exploited. And concerning the power consumption, a biasing is required for the macrobolometer, for the pyroelectric detectors, and for the TMOS, while the thermopile is self-biased. However, also in the case of the TMOS, since typically the transistor is operated in subthreshold, the power consumption still is pretty low. Now that I've given you a brief overview of the various types of thermal detectors, let's go more into detail on the case of the thermopile sensor, and particularly the one that I considered during my PhD for designing its interface circuit. This is the considered thermopile sensor, which was developed and fabricated by ST Microelectronics. It employed PN polysilicon as conductor material and consisted of 160 thermocouple elements placed in series. The absorbing membrane featured a 0.8 millimeters times 0.8 millimeter area made by an aluminum plate embedded in a dielectric membrane, which was released by a back dry edge. The responsivity is 180 volt over watts. The thermopile output resistance is 540 kilohms, and the thermopile sensor field of view without additional optics is 120 degrees. Given these characteristics, I developed interface circuit featuring a single-ended architecture. This was because in this way, there was no dependence of the amplification factor on the thermopile output resistance, which was quite large and would have required an even larger feedback resistance in order to achieve the desired gain if an inverting or differential configuration was used. And also there was the issue of having a resistance, the thermopile output resistance, which cannot be controlled. It depends on the sensor and its process variations. Then with this solution, no current flows through the thermopile, so there cannot be the Peltier effect, which basically causes a variation in the thermopile temperature when current flows through it. This is avoided, and also in this way the setting of the common mode voltage is straightforward by applying the common mode voltage VCM to one of the terminals of the thermopile. A closed loop was employed in order to have better control on the amplification factor, and of course chopper technique had to be applied in order to cancel the low frequency noise and offset of the amplifier, which would otherwise mask the signal provided by the thermopile. The chopping technique was applied only to the first stage of the amplifier because the second stage offset and noise referred to the inputs are negligible, consider that they are divided by the gain of the first stage. The first stage had a gain of around 60, with a gain of around 40 dB for the second stage. The chopping frequency was set to 2 kilohertz, which is around the corner frequency of the amplifier, which is a good compromise. Since if you have a higher chopping frequency, you will be able to cancel out more noise, but at the same time you will have more residual offset. So putting the chopping frequency at around the corner frequency is a good choice. The supply voltage was 1.2 volts, and the two resistances were 1 kilo and 99 kilo, thus providing an amplification factor of 100, considering that this is a non-inverting configuration for the amplifier. And finally, capacitances CC were added for stability. I mean, one was added for stability, the other one was added for symmetry reasons. So this type of chopper amplifier was inserted in the overall system and fabricated in a standard 130 nanometer CMOS process by ST Microelectronics. After this chopper amplifier, there was a passive low-pass filter with a 5 Hz cutoff frequency, which was used to filter out the offset and noise moved at the chopper frequency. And then there was also an output buffer to drive the output pad, which was connected with two switches, which were used to enable a test mode for the output buffer, during which the buffer offset could be measured, so it could be taken into account when the signal measurement was performed, in order to correctly estimate only the offset due to the interface circuit. This buffer was just used for testability purposes, indeed. Here we can see a summary of the performance of the proposed amplifier, which uses the lowest supply voltage and features the lowest overall power consumption. And as you can see, it has a very good input offset work case and standard deviation, especially considering that 29 chip samples were considered for making these statistics, which is more than double of what is used in the other cases. This is the measurement setup that was used in order to evaluate the proposed interface circuit together with the thermopile sensor. A heater was used as target object. It was covered in black paint, so its emissivity was evaluated as equal as to 0.95, which is comparable to the one of the human skin. And basically, by varying the voltage applied to the heater, it was possible to regulate its temperature, so that could be varied. And in particular, the temperature range of interest was between 20 and 45 degrees. The overall system, including the evaluation board, the thermopile sensor, the interface circuit test chip, and the heater, were placed in a metal box to reduce disturbances and environmental noise. And an IR thermometer was used to measure the ambient temperature and the target temperature. And also, of course, the buffer offset and common mode voltages were measured and subtracted to the other measurements. And for each considered target temperature, the measurement was performed averaging 100 samples and taken at 1.25 Hz rate by a multimeter. Here you can see the measurement results, considering a 3 centimeter distance between the target and the detector, so the heater and the detector, with the field of view 120 degrees, which is the unlimited field of view by the thermopile. And you can see here the output signal as a function of the temperature difference between the target object and the ambient, which is quite repeatable. And now what you see is that the electronic noise is determined in the case of a thermopile by the thermal noise associated to its output resistance. However, in a real case scenario, the dominant noise source is not electronic noise, but is the environmental noise and disturbances due to the fact that the sensor will pick up radiation from everything in its field of view. If we have a 120 degrees field of view, basically the sensor will pick up radiation from all its surroundings, not only from the target object. So the solution here has been to limit the field of view of the thermopile by adding a perforated metal cap, like the one shown in figure, so that the field of view of the thermopile could be completely filled by the target object, so by the heater. You can see here the measurements considering a 3 centimeter distance and the limited field of view by the metal cap, so roughly 52 degrees. And you can see here the output signal as a function of the difference between the temperature of the target and the temperature of the ambient. And you can also see the uncertainty associated with each measurement, so the standard deviation measured across 100 samples taken in that case. And if you take into account this uncertainty and the derived sensitivity from the graph, this yields that the plus minus 3 times the standard deviation is equal to plus minus 0.24 degrees, which is within the target specification, which was 0.3 for contactless human body temperature measurements. So also from the point of view of accuracy, the system satisfied the requirements. Then we consider another type of application, which is presence detection. We placed the sensor interface circuit system at a 132 centimeter height from the ground, and we mapped different positions in the room, and each position was identified by its distance from the sensor location and the angle alpha or minus alpha as shown in the figure with respect to the normal line to the sensor. And in this way, we try to see if there was a difference between the output signal when no person was placed in a certain position and when there was a person there. And if there was a difference, then that meant that we could detect the presence of the person. And as you can see from the mapped graph on the right, the positions with the cross on it means that in that position it was not possible to detect a difference in the signal. So those positions in those positions basically the sensor was blind to the presence of the person. In the other ones, the blue dots, the person could be correctly identified. If we look at the measurement results, considering only, let's say, the normal line to the sensor, we see that the stationary subject could be detected at up to 5.5 meter distance when the ambient temperature was 22 degrees. And as you can see here, this is a fit of the measured data, the output signal with respect to the distance. Then also the system was tested in order to verify if it could work for motion detection. And this is the result of a subject walking at 1 meter distance from the sensor by passing in front of it. As you can see, where there is the peak is the moment when the person is inside the sensor field of view, and the same measurements were repeated also considering a subject that was running or walking at a larger difference from the sensor. And as you can see, basically, if the subject is running in front of the sensor, the peak is very narrow because, of course, the person will be within the field of view of the sensor for a shorter time with respect to what happens when the person is walking. But anyway, still the peak was clearly identifiable in all cases, which means that the system worked properly for motion detection. Now, let's have a look at the second part of my talk, which focuses on the TMOS sensor and its developed interface circuit. As I mentioned before, the TMOS sensor is basically a suspended and thermally isolated transistor with an absorbing membrane on it, which collects thermal radiation and causes a local temperature difference on the sensor. Actually, each TMOS is made with a mosaic structure, so there are many pixels in particularly 64 pixel in an 8x8 matrix, which are connected in parallel and so act as an equivalent single transistor. And in each packaged device, which is packaged under vacuum in order to enhance the performance, there are actually two different TMOS transistors, where one is the so-called active device, so with the membrane which is exposed to radiation, and the other one which is a blind device because there is an aluminum mirror deposit on its package, so that it is not reached by the thermal radiation coming from the surroundings. In this way, basically, we have one active and one blind, so we have a fully differential configuration where the blind one is employed as, let's say, reference. Of course, as I mentioned before, the performance depends on the configuration used for the transistor, if it's used as a regular three-terminal transistor or if it's used in a diode configuration, and of course it depends on its operating point. In this case, we will use the transistor as a three-terminal device, and the responsivity was evaluated to be equal to 1.85 kilovolt over watts, which is one order of magnitude larger than what is achieved with the thermopile. But this is expected because the TMOS is an active device, so we have an intrinsic gain which will give us this benefit. As you can see, the TMOS can be represented, let's say, modeled with the small signal model of the regular transistor, with the addition of the ISIG terminal, which will be the additional, let's say, sensor current, which is determined by variation of the temperature, which will cause the variation in the current and so on. And of course, the temperature difference, the one that is called delta TMOS, that is the local temperature variation in the TMOS, will be proportional to the one that is found in the target by a certain coefficient that is TF, which in our case it's around 0.05, 0.05 round. And so we can see that the sensitivity of the target, when we consider the sensitivity for the output voltage, will be equal to minus the impedance of the TMOS, the TMOS times its sensitivity with respect to the current. As I mentioned, we will use the TMOS in a three-terminal configuration. So we will have basically the differential pair with the active and the blind TMOS, which will be biased by a current sink. So in this way, the common source node can move when gate voltage varies while maintaining the desired operating point. We will have a 1.2 supply voltage, and we will need to bias the gate accurately in order to, let's say, maintain the operating point that we want. In this case, the gate voltage needs to be equal to 520 millivolts. The bias current of the current sink is 2 microamps, so 1 microamp for each device, the active TMOS and the blind TMOS. And there is resistances are equal to 600 kilo ohm, which are used in order to set the common mode voltage at half the supply voltage. In these cases, what we see is that the simulated sensitivity with respect to the TMOS local temperature variations is minus 22.17 millivolts per degrees. Of course, since a variation in the TMOS is, as I said, proportional to the one of the target, but it's, let's say, reduced. What we see is that actually, if we look at the variation in the target, what we get is a simulated sensitivity of minus roughly 450 microvolt per degrees. In this case, we are not really exploiting completely the output impedance of the TMOS, because in this case, since the output impedance of the TMOS is in the mega ohm range, actually what is dominating is the resistance R. But we need this in order to be able to set a reasonable operating point for the TMOS. Okay, so here we see the bias circuit that I developed. As I showed before, we use the two terminals, the two TMOS with 3-terminal configuration with a current sink, which is given by the current mirror by transistors M1 and M2 with the ITMOS biasing current, and the two load resistances as shown. And we are interested in having as output signal the voltage, the difference between the two voltages found at the drains of the two TMOS transistors. However, we need to consider that there is process variation mismatches which will affect the two TMOS devices. So in the end, if we place exactly the same voltage at their gates, what we will have is that the two, even when there is no signal, the two drain voltages will be different. And so basically we will have a sort of offset that we do not want to have, because that would probably completely mask the signal we are interested in seeing. So for this reason, the approach was to vary one of the two gate voltages by generating the voltage through a current flowing through a resistor, where the current was controlled by a 9-bit current steering duct. In this way, we could adjust one of the two gate voltages while the other remained fixed, and we could eventually swap which one of the two gate voltages, if the one of the blind or of the active was to remain fixed, and the other vary, vice versa, in order to correct for process and mismatch variation in the fabrication. And the DAC resolution was 0.37 nanoamp, and this allowed us to achieve the desired, let's say, offset cancellation, as I will show you from measurement results later. For what concerns the interface circuit, in this case, we want to see the differential signal between basically the one provided by the active and the one provided by the blind. And so in this case, a differential approach was chosen, implementing a full differential instrumentation amplifier with 2 stages, an overall 100 dB open loop gain, and the gain was made selectable. That could be 20 or 30 for the amplifier. Actually, the overall gain could be 40 or 60 because the filter that was added for performing the modulation operation after the chopper provided an additional gain of 2, as well as the possibility to set the common mode independently from the common mode of the amplifier. So we could adjust also the amplifier in the case, the common mode voltage in the case, for example, the following ADC required a different one. As I mentioned, there is a chopper, as for the same reason as for the thermopile detector. We need to remove low frequency noise and offset. In this case, the chopping frequency was set to 1 kilohertz. And after the filter which performs the demodulation operation, we have an ADC, which is a standard 12-bit SAR ADC, which was designed by ST Microelectronics, which provides the digital output. Of course, we also wanted to be able to measure directly the analog output, and for these reasons, we placed 2 analog buffers with the same reasoning as the one employed for the thermopile. So with also the possibility of testing those and testing their offset separately in order to remove it from the overall measurement of the offset of the system. You can see here the test chip prototype, which was fabricated in the same technology used for the thermopile circuit interface, which is the 130 nanometer CMOS process by ST. And then the test chip and the TMOS sensor were mounted on the same ceramic package. Here we can see some measurement results. This is the mismatch correction for the TMOS. So basically, you can see here, in the case when no signal is applied, there was a mirror was used as target object, so that basically the same condition as the blind was applied to the active. And as you can see here, if by varying the code of the current-based DAC, we get a different output differential voltage, which is the basically the offset. And by correcting by selecting the correct DAC code, eventually we can go to have a residual mismatch error as low as 19 microvolts. This is the overall measurement setup. So we have the evaluation board with the microsystem package with both the TMOS and its interface circuit. We placed a black cardboard screen around it in order to limit disturbances coming from the surroundings, and we placed the heater on top of the black screen. And for the same reason as for the thermopile, it also in this case was necessary to limit its field of view, the field of view of the sensor, and this was used by a perforated metal cap. Here we can see the measurement results. When we considered the heater at 3 centimeter distance from the sensor and the limited field of view, which was roughly 50 degrees, which was determined by the perforated metal cap. As you can see here, the differential output voltage as a function of the difference between the target object temperature and the ambient temperature is quite repeatable. And then here we can see also the measured differential output voltage as a function always of the difference between the target object temperature and the ambient temperature, considering different distances. And as you can see here, basically the sensitivity stays the same, which is expected because with the limited field of view and those distances, the sensor field of view is completely filled by the target object. So this verifies what was I saying before at the start of this talk. And you can see here, so the sensitivity is around minus 11 millivolts per degrees. And as for the thermopile sensors, many measurements were acquired for each temperature case, and there was a certain uncertainty associated to it, considering its standard deviation. And if we consider in this case the worst case standard deviation, we consider plus minus three times those values and the sensitivity we measured, this yields to an accuracy of plus minus 0.17 degrees, which is improved with respect to the thermopile and well fits the requirements of the application of human body temperature measurements. We also verified the proposed system for presence detection by applying a person, by having the setup illustrated in the figure, so quite similar to the one used in the case of the thermopile. In this case, we used a stationary subject which was placed across along the normal line to the sensor at varying distances. And as you can see here are the data with the stationary subject that is detected up to 4.5 meters at a distance of 25 degrees, in ambient temperature of 25 degrees. And also, the system was tested for motion detection by moving a hand in front of the sensor, so mimicking a situation, for example, when we have an automatic soap dispenser and want to place the hand in front of it to get the soap without actually touching it. And also, we have the case of a subject walking in front of the sensor or running in front of the sensor for various differences, and you can always see the peak, which clearly identifies when the subject was present in front of the sensor. So concluding, we can have a comparison between the two systems I developed. And we can see that basically the technology was the same for the interface circuit. In the case of the TMOS, we had a different technology when considering the thermopile, when considering the TMOS, and one when considering its interface circuit. The area is larger, the one for the TMOS, because also we have to consider that we have the TMOS bias circuit, which is not necessary for the thermopile, which is self-biased. The supply voltage was more or less the same, apart from the ADC and digital block in the case of the TMOS, which require 1.8 supply voltage. The power consumption is lower in the case of the TMOS when we don't consider also the ADC, but the ADC was basically a standard general purpose ADC, which was developed in ST, was not optimized for these applications, so eventually its power consumption for sure can be lowered significantly. The chopper frequency is more or less the same, as is more or less also the readout gain. It's not orders of magnitude of difference. The sensor active area is smaller in the case of the TMOS, but yields a larger sensor responsivity because of the intrinsic gain of the TMOS I was mentioning. Of course, the problem with the TMOS is that you cannot really completely exploit its intrinsic gain because otherwise you would not be able to really control its operating point. Eventually you need to fix its bias some way, and if you place the most straightforward, more controllable way is to place a resistor as load, and that resistor will be lower than the output resistance of the TMOS. So for sure that will limit its intrinsic gain. The distance was the same as the sensor field of view. As you can see, the sensitivity is better in the case, and the accuracy are better in the case of the TMOS. The disadvantage of the TMOS is that it's pretty slow. It has a larger response time with respect to the thermopiles. And the distance at which the system worked properly for presence detection was, let's say, comparable at the end. By looking at these two types of sensor, what we see is that for sure the thermopiles are very inexpensive, perform well, are very low power. From the point of view of performance, the TMOS can be better. And this, I think, is for now. Also, I know that ST has been developing. It's already commercially available. A solution exploiting the TMOS with the for presence detection. The next step will be to try and exploit the TMOS also for absolute temperature measurements. For sure, it looks very, very promising. So with this, I have concluded my talk. Here you can see my email address, so you can also contact me if you're interested in the topic or other topics. I've let's say I've been working on very different topics in the last couple of years. I'm moving towards integrated power management, and let me say that in our research group in Pavia, at the Integrated Microsystem and Sensors Lab, we are always looking for talented people. So if you're interested, please contact me. We have open calls for PhDs with grants for the let's say starting in April. So let me know if you're interested, and I will be happy to reply to your questions.
Thank you very much, Elisabetta, for this very nice talk. So I see some questions here in the chat. So first one by Elias Ramos. Thank you very much for the presentation. It was a very interesting topic. I'd like to know if the effect of noise, such as random telegraph noise, was studied in your work.
Thank you for the question. As I mentioned before, when you're dealing with thermal detectors, let's say in real case scenarios in real life, what you see is that electronic noise and so on are not the problem anymore. The problem is all the noise that comes from the ambient. Because think about having the detector in a certain place. You say, okay, I'm interested to see if, for example, my hand is moving in front of it or not, if it detects its presence. Yes, but then you have, for example, the lights in the room that will also change. Basically, they will emit radiation. They will change the outcome if you have that the light is caught by the sensor or not, if there is light or not. So I did not do an analysis on this kind of topics, because in the end, what I have seen from my experience with the thermopile, which was, let's say, quite easy to know from the point of noise, because it's basically an equivalent resistor from the point of electronic noise. What I've seen then when I was doing the measurement was that my problems were not electronic noise, was these other types of noise, and basically the solution in that case is just to limit the field of view to try and catch just what you want.
Thank you very much. So another question by Elias regarding presence detection, motion detection. Has any approach using machine learning been considered?
Wow, this is a really nice suggestion. I did not consider that because it's, let's say, I've done this work during my PhD. Basically, let's say I was the main researcher, and of course, I had support from the company and from my supervisors, but it was not done, let's say, in a large team. But of course, in order to be to really let's say exploit the potential of this type of in this type of applications, such as presence detection, motion detection, I think machine learning is used. But as I said, let's say I did not use it during my research. I was more interested in the, let's say, circuit level, interface circuit level stuff.
Okay, thank you. I see no more questions here in the chat. So if someone still have a question, please do it very urgently. So I have one. Do you have also considered some aspects of reliability considering radiation effects?
Well, in the applications I was considering, we were always considering cases where, okay, we are in, let's say, in a regular room type of setting. So we have people, we are not, these type of sensors are not used when you have like high radiation. It's just, let's say, regular setting. So I did not um, investigated that, but thermal detectors can for sure be used also in those kind of applications. Maybe not
Okay.
these types, really.
Yeah. Okay. Thank you, Elisabetta, for your very
Thank
nice
you.
talk. I see no
Thank
more
you very much for
questions
the invite.
here. Thank you very much. So before ending the sessions, just some announcements. If you lost some of the talks that are being done since mid 2020, you can see all them in this YouTube channel. Sometimes you have to search because in YouTube they limit some number of talks by row, and so. But if you do a search, you can see all the list of talks that are available. Also, the next soon we are going to announce the next CASS talk. And just to remind you also that you have 2 weeks to submit your papers to next edition of LASCAS in the beautiful Bento Gonçalves, the most traditional wine region in south of Brazil, close to Porto Alegre. So see you soon in the next CASS talk. So thank you very much to all the audience, and mainly thanks to Elisabetta for the nice talk that was given today. So bye bye.